In 1994, a chain of ice and rock fragments hit Jupiter over 6 days. The largest piece was 2 kilometers across. It was moving at 216,000 kilometers per hour when it struck. The blast from that single fragment released energy equivalent to 600 times the combined nuclear arsenal of every nation on Earth. The debris plume rose 3,000 kilometers above the cloud tops and left a dark scar wider than our entire planet. And here is what should genuinely unsettle you. Jupiter gets hit by something that size roughly once every 6,000 years. Earth got hit 66 million years ago and it ended the age of dinosaurs. The gap between those two numbers might be the reason you exist. Because Jupiter, sitting out there past the asteroid belt like an enormous gravitational sentry, may be catching or deflecting a significant fraction of the objects that would otherwise come screaming into the inner solar system and hit us. Most people filed Jupiter away after grade school: big planet, stripes, red spot, many moons. And that is a shame, because Jupiter is arguably the most important planet in the solar system. Its moon Europa almost certainly has a saltwater ocean beneath its ice that contains more liquid water than every ocean on Earth combined. Scientists are sending spacecraft there right now because they think something might be alive in that water. Jupiter is where the biggest unanswered questions in planetary science are concentrated, and we are going to take it apart layer by layer, moon by moon, mystery by mystery. Jupiter does not orbit the Sun, not in the simple way you were taught. The Sun and Jupiter orbit each other around a shared point in space called a barycenter. Every pair of orbiting objects has one. It is the center of mass of the system, the balance point. For most planets, the barycenter sits deep inside the Sun, so far inside that the distinction between the planet orbits the Sun and they orbit each other is meaningless. Earth's barycenter with the Sun is about 450 kilometers from the Sun's center. The Sun's radius is 696,000 kilometers. The barycenter is buried so deep inside the Sun that it might as well not exist. Jupiter is different. Jupiter is so massive and so far from the Sun that the barycenter between the two of them sits outside the Sun's surface. It floats above the photosphere out in open space at about 1.068 solar radii from the Sun's center. What this means in practical terms is that as Jupiter swings around on its 12-year orbit, the Sun wobbles. It traces a small loop in space, dragged around by a planet that has 1,000th of its mass. 1,000th sounds insignificant until you consider the accounting. The Sun holds 99.86% of all the mass in the solar system. Every planet, moon, asteroid, comet, and grain of dust shares the remaining 0.4%. Its mass is about 2.5 times greater than all the other planets combined: Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune. Add them all up. Jupiter still outweighs the lot by a factor of 2.5. This is not just a fun fact. This wobble is one of the primary methods astronomers use to detect planets around other stars. When a distant star appears to drift slightly back and forth in a rhythmic pattern, we know something massive is pulling on it. The technique is called the radial velocity method, and it has led to the discovery of hundreds of exoplanets. Jupiter, in a very real sense, taught us how to find worlds orbiting other suns. Now let us set the scene. Where does Jupiter actually sit in the solar system? Moving outward from the Sun, you pass Mercury, Venus, Earth, Mars, and then the asteroid belt, that broad ring of rocky debris left over from the formation of the solar system. On the far side of the belt sits Jupiter, the first of the outer planets. Its average distance from the Sun is about 778 million kilometers, or 5.2 astronomical units. 1 astronomical unit is the Earth-Sun distance. So Jupiter is more than 5 times farther from the Sun than we are. Sunlight takes about 43 minutes to reach Jupiter, compared to roughly 8 minutes to reach Earth. By the time that light arrives, it has spread out enough that Jupiter receives only about 4% of the solar energy per square meter that Earth does. Despite that distance, Jupiter completes one orbit every 11.86 Earth years. If you were born on Jupiter, you would celebrate your first birthday only after nearly 12 years had passed by Earth's calendar. Jupiter's axial tilt is only about 3.1 degrees. Earth's is 23.4 degrees, Mars has 25.2. That tiny tilt means Jupiter does not experience meaningful seasons. There is no summer hemisphere, no winter hemisphere. The planet presents itself to the Sun at nearly the same angle year after year, century after century. Whatever drives Jupiter's atmosphere, it is not seasonal change. It is something else entirely, and we will get to that. The planet spins fast, absurdly fast for its size. One full rotation takes just under 10 hours. Jupiter has a diameter roughly 11 times that of Earth. A volume you could pack 1,300 Earths inside, and it completes a day in less time than it takes to fly from Los Angeles to London. That rotational speed has a visible consequence. Jupiter is not a sphere. It is an oblate spheroid, bulging at the equator and flattened at the poles. The equatorial diameter is about 143,984 kilometers. And Jupiter is one of the best targets in the sky for amateur astronomers. When it is well placed, it can be the third brightest natural object visible at night, after the Moon and Venus, reaching an apparent magnitude of about -2.94. At that brightness, it can cast faint shadows on a dark night. Through a consumer telescope, you can see the cloud bands, sometimes the great red spot and the 4 Galilean moons as tiny bright points flanking the planet. People have been watching Jupiter for thousands of years. The Babylonians tracked it. The Romans named it after the king of their gods. In January 1610, Galileo pointed a crude telescope at it and saw 4 moons orbiting a world that was not Earth, and the entire cosmological framework of Western civilization began to crack. Let us talk about mass and gravity, because Jupiter's mass is not just a number, it is a force that reshapes the entire solar system. Jupiter's mass is approximately 1.898 times 10 to the 27th power kilograms. Earth's mass is about 5.97 times 10 to the 24th power kilograms. Jupiter is roughly 318 times more massive than Earth. Its diameter is about 11 times Earth's. Its volume is about 321 times Earth's. But its density is only about 1.33 grams per cubic centimeter, less than a quarter of Earth's density. If you could somehow find a bathtub large enough, Jupiter would float. It would float poorly, mostly submerged, but it would float. Earth would sink like a stone. Jupiter is the most massive planet, but not the densest. That distinction goes to Earth. If you took Neptune and inflated it to Jupiter's size while keeping its density, it would be more massive than Jupiter. And if you compressed Jupiter down to Earth's size while keeping its density, Earth would be over 4 times more massive. The reason Jupiter is the heavyweight of the solar system is simply that it is enormous, not that it is made of particularly dense stuff. But mass is mass, and mass creates gravity, and Jupiter's gravity is consequential on a solar system scale. The surface gravity of Jupiter is about 2.53 times Earth. Stand on the cloud tops, if such a thing were possible, and you would weigh 2.5 times what you weigh at home. That gravity is strong enough to capture and hold at least 95 known moons. It is strong enough to tear asteroids apart through tidal forces. It is strong enough to create and maintain the Kirkwood gaps in the asteroid belt, those orbital zones where asteroids cannot survive because Jupiter's gravitational resonances destabilize their orbits. Some scientists believe Jupiter prevented a planet from forming in the asteroid belt altogether. The gravitational stirring from the giant planet kept the material there too agitated to coalesce. Instead of a fifth terrestrial planet, we got a belt of debris, and the largest object in it, the dwarf planet Ceres, has less than 1/3 of 1% of our Moon's mass. Jupiter's influence reaches further still. There is a compelling argument that Jupiter acts as a partial shield for the inner solar system. The idea is that Jupiter's gravity either captures or deflects many long-period comets and stray objects that might otherwise reach Earth's neighborhood. Jupiter receives an estimated 2,000 to 8,000 times as many cometary impacts as Earth, partly because it is a much bigger target and partly because its gravity actively attracts objects. Some of those objects, if Jupiter were not there, might have continued inward toward the terrestrial planets. This argument is part of the rare Earth hypothesis, which suggests that the conditions necessary for complex life may require, among other things, a large gas giant in the right orbital position to reduce the impact rate on habitable worlds. Not everyone agrees. Some models suggest Jupiter can redirect certain objects toward the inner solar system as well as away from it, potentially increasing the impact risk in some scenarios while decreasing it in others. The net effect is complicated and depends on the specific population of objects being considered, but the debate itself illustrates how deeply Jupiter's gravity reaches into the question of whether life can exist. There's even a prediction, based on computational models, that Jupiter's gravitational perturbations may eventually destabilize Mercury's orbit. Mercury already has the most eccentric orbit of any planet in the solar system. Over billions of years, the cumulative nudges from Jupiter could push that eccentricity past a critical threshold. Mercury could theoretically crash into the Sun, collide with Venus, or be ejected from the solar system. This is not expected for billions of years, and it may never happen at all. But the fact that a planet 5 times farther from the Sun can threaten Mercury's existence tells you everything you need to know about the reach of Jovian gravity. Now the atmosphere. This is where Jupiter stops being a number and becomes a visual spectacle. The first thing you notice looking at Jupiter through any telescope is the banding. Alternating light and dark stripes wrap the planet parallel to its equator in shades of white, cream, tan, orange, brown, and reddish brown. These bands have been observed and catalogued for centuries. The light bands are called zones, the dark bands are called belts. Between them blow jet streams that reach speeds of over 600 kilometers per hour, running in alternating directions. Where zones and belts meet, the shearing winds create turbulence, vortexes, and storms. The visible cloud layer is made primarily of ammonia ice crystals. It is surprisingly thin, only about 50 kilometers deep. That is remarkably shallow for a planet with a radius of roughly 70,000 kilometers. Everything you see when you look at Jupiter, every swirl and band, is happening in a shell thinner relative to the planet than the skin of an apple is relative to the apple. Below the ammonia ice layer, there is thought to be a layer of ammonium hydrosulfide clouds, and below that a layer of water clouds. The water layer has been frustratingly difficult to confirm observationally. It is one of the ongoing targets of investigation. The colors are a long-standing puzzle. Pure ammonia ice clouds should be white, and the freshest, highest altitude clouds are indeed bright white. But the reds, oranges, and browns that give Jupiter its character come from compounds called chromophores. The leading theory is that material from deep in Jupiter's atmosphere containing sulfur, phosphorus, and various organic molecules rises to the cloud tops where it is exposed to ultraviolet light from the sun. The UV radiation breaks apart and recombines these molecules into new compounds that absorb certain wavelengths of visible light. The longer the material sits in sunlight, the redder it gets. This is conceptually similar to photochemical smog on Earth. Sunlight reacts with pollutants to create brownish haze over cities. On Jupiter, the process operates on a planetary scale. Despite decades of study and multiple spacecraft missions, the specific molecules responsible for Jupiter's coloration have never been definitively identified. Laboratory experiments can create reddish-brown substances by irradiating mixtures of ammonia, methane, and hydrogen sulfide that somewhat match Jupiter's hues, but the exact recipe remains unknown. The appearance of the bands changes over time, sometimes dramatically. Belts and zones can widen, narrow, shift color, or temporarily vanish. In 2010, Jupiter's south equatorial belt, one of the two most prominent dark stripes, faded to near invisibility, leaving the planet looking oddly asymmetric for months before it gradually returned. But despite these surface changes, the latitudes of the bands remain remarkably stable. The boundaries between belts and zones are anchored at specific latitudes and do not drift north or south. This stability indicates that the jet streams defining the banding pattern are not shallow atmospheric phenomena, they are rooted deep inside the planet. How deep? Juno answered that question. 3,000 kilometers deep, the differential rotation visible at the surface, where different latitudes spin at slightly different speeds, persists to roughly 3,000 kilometers below the cloud tops. Below that depth, the planet rotates as a rigid body, everything moving together, locked by the magnetic field generated in the electrically conducting interior. 3,000 kilometers is not a thin atmospheric veneer, it is a substantial fraction of the planet's 70,000 kilometer radius. And then there is the Great Red Spot. Every person who has ever seen a picture of Jupiter knows this feature, a giant oval of swirling rust-colored clouds, large enough to swallow Earth with room to spare. It is the most famous storm in the solar system, and it has been raging continuously for at least 2 centuries, possibly more than 3.5 centuries. The Great Red Spot was first definitively observed in the 17th century. Robert Hooke described a spot on Jupiter in 1664. Giovanni Cassini tracked what may have been the same feature beginning in 1665. Whether the spot from the 1660s is the same storm we see today is debatable. Continuous observations extend back with certainty to at least the early 19th century. That means at minimum, this single storm has persisted for more than 200 years. On Earth, hurricanes last days to weeks. They weaken when they hit land, encounter cold water, or are disrupted by wind shear. The Great Red Spot has none of these problems. Jupiter has no land, there is no cold surface to drain energy. The storm sits between two opposing jet streams that simultaneously trap it in place and feed energy into it. It is an anticyclone rotating counterclockwise in Jupiter's southern hemisphere, locked in position like a ball bearing between two conveyor belts running in opposite directions. At its largest recorded size, the Great Red Spot was about 40,000 kilometers across, more than 3 times Earth's diameter. It has been shrinking. Voyager measured it at about 23,000 kilometers in 1979. By 2014, it was roughly 16,500 kilometers. The rate of shrinkage appears to be accelerating, and some scientists have speculated the spot could vanish within our lifetimes. Though predicting the death of a phenomenon we do not fully understand is a risky proposition. The color varies enormously. It can be deep brick red, pale salmon, or nearly white. The most current hypothesis is that the Great Red Spot rises higher than the surrounding clouds, exposing its material to more intense UV radiation for longer periods, producing more vivid chromophore coloration. When the spot appears pale, a layer of bright ammonia ice may have formed on top, hiding the reddish material beneath. Juno flew directly over the Great Red Spot and pointed its microwave radiometer downward. The instrument can probe to about 350 kilometers below the visible cloud tops. The Great Red Spot extends at least that deep, and the instrument could not find the bottom. The storm is not a shallow surface feature. It is a deep-rooted atmospheric structure reaching into regions of extreme temperature and pressure. Juno also found that the spot is cooler than its surroundings in the upper layers, but warmer below about 80 kilometers depth. This deeper warmth may be the engine driving the storm. The Great Red Spot is not alone. In the late 1990s, three smaller white oval storms that had existed since the 1930s merged. By 2000, they had combined into a single storm. In 2006, it turned red and was nicknamed Red Spot Junior, formerly known as Oval BA. It is about half the size of the Great Red Spot and has persisted for over 2 decades, including a close pass by its larger neighbor that might have destroyed it but did not. A different, smaller storm that took a similar path was not so fortunate. It was absorbed by the Great Red Spot and torn apart. At the poles, the storm architecture becomes bizarre. Juno's infrared cameras revealed geometric arrangements of cyclones that no model had predicted. At the South Pole, a central cyclone is surrounded by 5 others in a roughly pentagonal pattern. At the North Pole, a central cyclone is encircled by 8 others arranged roughly as an octagon. Each individual cyclone is comparable in size to the continental United States. They have remained in these geometric configurations throughout the entire duration of Juno's observations. Why cyclones on Jupiter arrange themselves in tidy geometric patterns while cyclones on no other planet do, this is not understood. Saturn has a single hexagonal jet stream at its north pole and a single vortex at its south pole. Jupiter apparently plays by different rules. Now let us go beneath the clouds, because what happens inside Jupiter makes the surface weather look straightforward. Before Juno, the standard model of Jupiter's interior was relatively neat, a thin atmosphere of hydrogen and helium on top. Below that, hydrogen gas gradually transitioning to liquid hydrogen as pressure increased with depth. Deeper still, at pressures millions of times Earth's atmospheric pressure, the hydrogen was believed to become metallic hydrogen, a state where molecules break apart and electrons flow freely, making the material electrically conductive. At the very center, a solid core of rock and ice, perhaps 10 to 20 Earth masses. Juno overturned most of this. The atmosphere extends to 3,000 kilometers, not a few hundred. Below that, instead of a gradual gas to liquid to metal transition, the planet is dominated by a vast ocean of metallic hydrogen making up 80 to 90% of the radius. Calling Jupiter a gas giant is technically inaccurate. Most of it is liquid. Or more precisely, most of it is an electrically conducting plasma with properties somewhere between a metal and a liquid. It probably looks and flows something like mercury, though no human has ever seen metallic hydrogen under sustained conditions and no laboratory on Earth has been able to create it reliably. The pressures required are staggering. Some experiments using diamond anvil cells have claimed brief detections at pressures above 400 gigapascals, but the results are controversial. Jupiter does this naturally, effortlessly across a volume larger than most planets. The core was the biggest surprise. Instead of a well-defined nugget of rock and iron at the center, Juno's gravity data points to what scientists call a dilute or fuzzy core. The heavy elements that were expected to form a concentrated sphere appear to be mixed in with the metallic hydrogen, spread out over a region extending perhaps 30 to 50% of the planet's radius. The boundary between core and envelope is not a sharp line, but a gradual gradient. One hypothesis is that a compact core formed early, but has been slowly dissolving over billions of years, its heavy elements diffusing upward. Another is that Jupiter never formed a clean core in the first place. This matters for the broader question of how giant planets form. The standard core accretion model says a rocky core grows to about 10 Earth masses, at which point it is large enough to gravitationally capture a massive envelope of hydrogen and helium gas. If Jupiter's core is dissolved or diffuse, the formation story may need significant revision. This has implications not just for Jupiter, but for every giant planet we discover around other stars. The overall composition of Jupiter is roughly 90% hydrogen and 10% helium by number of atoms, with trace amounts of methane, ammonia, water, hydrogen, sulfide, and other compounds. This is similar to the composition of the Sun, both formed from the same primordial cloud of gas and dust about 4.6 billion years ago. The difference is mass, which brings up the question that everyone asks at some point: could Jupiter have become a star? No, not remotely close. To sustain hydrogen fusion, the process that powers stars, a body needs to be roughly 75 to 80 times Jupiter's current mass. That is the minimum required to produce the core temperatures and pressures necessary for hydrogen nuclei to fuse. Jupiter would need to be approximately 75 times heavier to become even the faintest, coolest type of star, a red dwarf. There is a category of objects between gas giants and true stars called brown dwarfs, occupying the range of roughly 13 to 80 Jupiter masses. Brown dwarfs can fuse deuterium, a heavy isotope of hydrogen, but cannot sustain regular hydrogen fusion. Jupiter falls well below even the brown dwarf threshold. It is a planet. It was always going to be a planet. That said, Jupiter does emit more energy than it receives from the Sun, about 1.6 to 1.7 times more. Two mechanisms account for this. First, Jupiter is still slowly contracting under its own gravity, converting gravitational potential energy into heat. It shrinks by perhaps a few centimeters per year. Second, helium is gradually separating from hydrogen in the interior. Helium is denser, so it sinks, releasing gravitational energy as it falls through the metallic hydrogen. This process, sometimes called helium rain, is as alien as it sounds. Droplets of helium falling endlessly through an ocean of liquid metal inside a planet where the pressure would obliterate any material human beings have ever made. This internal heat drives Jupiter's weather. Unlike Earth, where the Sun powers the atmosphere, Jupiter's atmospheric dynamics are powered from below. The planet is essentially a furnace, radiating heat upward, driving convection, generating the bands and storms that we see from the outside. This is why the absence of seasons does not matter. Jupiter does not need the Sun to power its weather. It brings its own energy. A quick note on something most people do not know: Jupiter has rings. They are nothing like Saturn's magnificent ice rings, and you will never see them through a backyard telescope discovered by Voyager 1 in 1979. Jupiter's ring system consists of 4 components. The main ring is about 6,500 kilometers wide, extremely thin and very faint. Unlike Saturn's rings, which are mostly water ice, ranging from tiny grains to house-sized chunks, Jupiter's rings are composed of microscopic dust particles produced by micrometeorite impacts on Jupiter's small inner moons, primarily Metis and Adrastea. A diffuse halo ring extends inward. 2 broader, even fainter gossamer rings extend outward, fed by dust from the moons, Amalthea and Thebe. Without the moons continuously generating fresh dust, the rings would vanish within thousands of years. They are a dynamic, transient feature in constant creation and destruction. Now the magnetic field. This is where Jupiter stops being impressive and becomes genuinely dangerous. Jupiter's magnetic field is the most powerful of any planet in the solar system. At the cloud tops, it is roughly 20,000 times stronger than Earth's. The magnetosphere it generates extends tens of millions of kilometers into space. If you could see it with your naked eye from Earth, it would appear larger than the full moon. The magnetotail, the downstream streamer of the field stretched by the solar wind, extends past the orbit of Saturn, more than 600 million kilometers from the planet. It is the largest coherent structure in the solar system after the heliosphere itself. The field is generated in the metallic hydrogen interior. The planet's rapid rotation combined with convective motions in the electrically conducting fluid produces a dynamo effect. The resulting field is roughly dipolar, like a bar magnet, but with significant irregularities. Juno mapped these irregularities in unprecedented detail and discovered something fascinating, a concentrated patch of magnetic flux near Jupiter's equator that scientists named the Great Blue Spot. By comparing Juno's measurements with data from Pioneer, Voyager, and Galileo, scientists discovered that Jupiter's magnetic field is changing over time. The Great Blue Spot appears to be drifting. This was the first detection of secular variation, meaning gradual change in any planetary magnetic field other than Earth's. Juno also found a previously unknown radiation belt hugging the planet just above the equatorial cloud top. This inner belt is less intense than the main radiation belt farther out, but its existence was completely unexpected. The mechanisms creating it are still being investigated. The main radiation belts are a nightmare. Within the most intense zones, the radiation would deliver a lethal dose to an unshielded human within hours. Every spacecraft that has operated near Jupiter has suffered radiation damage. The Galileo orbiter experienced progressive instrument degradation over its 8 years in the system. Juno's polar orbit was specifically designed to thread through a gap between the atmosphere and the inner edge of the main radiation belt, minimizing exposure. Even so, the cumulative dose is gradually wearing the spacecraft down. This is ultimately what will end the mission. The magnetosphere also creates permanent auroras at Jupiter's poles. They are visible primarily in ultraviolet and infrared wavelengths. Total radiant power about 100 terawatts. The total electrical generating capacity of the United States is roughly 1 terawatt. Jupiter's auroras output 100 times that, running continuously, never stopping on Earth. Auroras are episodic, triggered by solar storms. On Jupiter they are permanent. They are powered by the rotation of the massive magnetosphere, by the solar wind, and by charged particles injected into the system by the volcanic moon Io. Juno found that the auroral emissions are driven primarily by alternating currents rather than direct currents, which required a revision of existing models. The auroral structure differs between the poles. At the North Pole, where the magnetic field lines are more complex and tangled, the aurora appears as scattered filaments and flares. At the South Pole, where the field is smoother, the aurora forms a more structured oval. Bright spots within the auroral display mark the magnetic footprints of the Galilean moons. The brightest spot belongs to Io, connected to Jupiter by the Io flux tube, an enormous electric current flowing along magnetic field lines. Europa and Ganymede leave fainter marks. Each bright spot represents a current carrying millions of amperes at hundreds of thousands of volts. Let us now look at Jupiter through wavelengths of light beyond what human eyes can see, because some of the most valuable science comes from invisible radiation in the thermal infrared around the 5-micron wavelength. You see Jupiter's own heat escaping from deep inside the planet. The image looks nothing like the familiar striped sphere. Bright patches show where the cloud deck is thin and heat escapes easily. Dark patches show where thick clouds trap the heat below. The relationship is often reversed from visible light. The dark belts that appear dark in visible light because they are lower and less reflective are often bright in infrared because the sinking air has cleared the upper clouds, creating thermal windows. The bright zones in visible light, where rising air builds thick cloud layers, are dark in infrared because those thick clouds insulate against the escaping heat. The Great Red Spot, being the highest and densest cloud structure on the planet, appears as one of the darkest features in thermal infrared. Its thick clouds block nearly all the heat from below. Juno's infrared aurora mapper provided three-dimensional views of the polar cyclones that are simply stunning. Because infrared shows heat rather than reflected sunlight, haze and high-altitude clouds do not obscure the view. The temperature differences between cyclones are visible. The warmer, lower regions glow brightly. The colder, higher features are dark. Even by Jupiter standards, the temperature range is cold. The warmest areas in the polar images are only about -3 degrees Celsius. The darker, high-altitude regions reach -83 degrees Celsius. In the near-infrared, specific absorption bands reveal different atmospheric components at 2.17 microns. Hydrogen absorbs strongly. When you view Jupiter at this wavelength, the hydrogen atmosphere becomes opaque and only the very highest clouds, those poking above most of the atmospheric hydrogen, remain visible. At 3.01 microns, methane and ammonia dominate the absorption. Each wavelength gives a different slice through the atmosphere, and by combining them, scientists build three-dimensional maps of atmospheric structure. This multi-wavelength approach works on the moons as well. Europa, observed at the 1.5 micron water absorption band, reveals the distribution of water ice on the surface. Regions of pure water ice look distinctly different from regions where ice is mixed with other minerals. Think of these images less as photographs and more as chemical maps, with colors chosen to represent the abundance of specific molecules detected through spectroscopy. Spectroscopy is extraordinarily powerful. Every molecule absorbs and emits light at unique wavelengths, creating a spectral fingerprint. By analyzing the light reflected from a planetary surface, scientists can identify what molecules are present without landing there. Spectroscopic observations of Europa have detected sulfuric acid concentrated around surface fractures and on the trailing hemisphere. The fracture deposits may come from the ocean below. The trailing hemisphere deposits are attributed to bombardment by sulfur ions from the plasma torus, material that originally erupted from volcanoes on Io. One moon's volcanic output is chemically modifying the surface of another moon across millions of kilometers of space. On Callisto, infrared data overlaid on visible light crater images shows patterns of water ice distribution. In one well-studied example, the crater center is icy, surrounded by a ring of ice-poor material, surrounded in turn by icy debris in a ray system extending outward. The impact excavated ice from beneath a thin surface layer of darker material. The debris formed the icy rays. Why there is an ice-poor ring between the crater center and the ray system is not fully explained. In the ultraviolet, Jupiter's auroras are the dominant feature. Hubble has monitored Jovian auroral emissions for years. Ultraviolet proved particularly useful in 1994 when comet Shoemaker-Levy 9 struck Jupiter. The dust from the impacts absorbed UV sunlight, allowing scientists to track wind patterns in Jupiter's stratosphere by watching how the impact debris dispersed over time. Let us talk in detail about that impact, because it was one of the most consequential astronomical events in modern history, and its implications reach far beyond Jupiter. In March 1993, astronomers Caroline Shoemaker, Eugene Shoemaker, and David Levy were conducting observations at the Palomar Observatory in California when they discovered an unusual comet. It was not orbiting the Sun, it was orbiting Jupiter, captured by the giant planet's gravity at some point in the past. It was fragmented, likely torn apart by Jupiter's tidal forces during a previous close approach, probably in July 1992, and its orbit was extraordinarily eccentric, with an eccentricity above 0.998, barely bound to Jupiter at all. Almost immediately, orbital calculations revealed a troubling possibility. The comet, designated Shoemaker-Levy 9, was on a collision course with Jupiter. The impact would occur in July 1994. Pretty soon the prediction was confirmed and the whole astronomical community began preparing. Telescopes around the world were pointed at Jupiter. The Keck Observatory, the Hubble Space Telescope, Germany's Rosat X-ray Telescope, and many others allocated time. But there was a problem. The geometry of the comet's approach meant the impacts would occur on the far side of Jupiter, the hemisphere facing away from Earth. Ground-based telescopes and Hubble would not be able to see the actual moment of collision. Then fortune intervened. NASA's Galileo spacecraft, launched in 1989 and still about a year from reaching Jupiter, happened to be positioned at an angle that gave it a direct line of sight to the impact zone. The Ulysses spacecraft, launched in 1990 to study the Sun, was also oriented toward Jupiter. Even Voyager 2, by then 44 astronomical units away, was programmed to monitor radio emissions from the event. 3 spacecraft paused their own missions to work together on capturing an event that no human had ever witnessed. On July 16, 1994, fragment struck Jupiter. Galileo recorded a massive fireball erupting from the planet, reaching temperatures estimated at 24,000 degrees Celsius. The debris plume rose 3,000 kilometers above the cloud tops, roughly the north-south extent of Australia. When Jupiter's 10-hour rotation brought the impact site into Earth's view, telescopes saw a huge dark scar on the planet, visible even through modest amateur instruments. For 6 days between July 16th and July 22nd, the comet's 21 fragments hammered Jupiter. The largest impact, fragment G on July 18, was the most destructive. It alone released energy equivalent to about 600 times the world's entire nuclear arsenal. The dark scar it left was roughly 1 Earth diameter across. But not every impact was equally devastating. The fragments ranged in size, with the largest estimated at about 2 kilometers in diameter. The bombardment heated Jupiter's atmosphere to 30,000 degrees Celsius at the point of impact. Shock waves rippled outward through the atmosphere at 450 meters per second. The dark scars from the impacts were visible for months, slowly dispersing as atmospheric winds spread the debris. The aftermath was as scientifically valuable as the explosions. The impacts punched through Jupiter's cloud tops and excavated material from deeper layers. Spectroscopic analysis of the debris clouds detected diatomic sulfur, carbon disulfide, ammonia, and hydrogen sulfide. Heavy elements including silicon, iron, and magnesium were found, probably from the comet itself. And surprisingly, water. Significant water vapor was detected in the debris, though scientists debated whether it came from Jupiter's atmosphere or from the comet's ice. The question of how much water Jupiter contains and where it hides remains one of the major open questions in planetary science and was a primary motivation for the Juno mission. The impact had immediate and lasting effects on science and policy. Before 1994, there was no systematic effort to catalogue near-Earth objects. The term planetary defense did not exist. Shoemaker-Levy 9 made it viscerally clear that destructive impacts on planets are not just ancient history, they happen now. NASA established programs to identify and track asteroids and comets that could threaten Earth. The initial goal was to find 90% of near-Earth objects larger than 1 kilometer in diameter, a size above which an impact could cause global catastrophe. That goal has been largely achieved. The current focus has shifted to objects as small as 140 meters. The impact energized the rare Earth hypothesis argument. If Jupiter gets hit by something this size every 6,000 years, and Earth every 60 million years or more, and if Jupiter's gravity is partly responsible for deflecting objects that would otherwise reach the inner solar system, then having a massive gas giant in the right orbital position might be one of the prerequisites for complex life to evolve on a habitable world. This remains debated, as I mentioned earlier, but the Shoemaker-Levy 9 event moved the debate from theoretical to urgently practical. A comet of similar size striking Earth would likely end civilization and most complex life on the planet. We can be grateful that events of that magnitude appear to be extremely rare for Earth, separated by tens of millions of years. Whether Jupiter deserves partial credit for that rarity is still being investigated, but there is something reassuring about knowing that the biggest planet in the solar system is out there catching punches from the cosmos on a regular basis. In 2009, 2010 and 2012, amateur astronomers detected bright flashes on Jupiter from impacts by objects roughly 10 meters across. Jupiter takes a beating, so we might not have to. Now let us turn to the moons, all 95 known as of the latest surveys, though the number keeps growing. Most are small captured asteroids and comets orbiting far from the planet in irregular inclined, sometimes retrograde orbits. The ones that matter, the ones rewriting textbooks and motivating billion-dollar missions, are the 4 Galilean satellites: Io, Europa, Ganymede, Callisto. Discovered by Galileo in 1610, these 4 worlds orbit close to Jupiter in nearly circular equatorial orbits. They range from roughly the size of Earth's moon to larger than the planet Mercury. Each one is utterly different from the others, and each one presents its own set of scientific puzzles. We will take them from innermost to outermost. Io is violence made geological. It is the innermost of the 4 large moons, orbiting only about 350,000 kilometers above Jupiter's cloud tops. From Io's surface, Jupiter would dominate the sky, appearing 39 times larger than our moon does from Earth. One orbit takes 42.5 hours. Io is tidally locked, always presenting the same face to Jupiter. That proximity defines everything about this world. Jupiter's tidal forces flex Io as it moves through its slightly eccentric orbit. The orbit is kept eccentric by the gravitational influence of Europa and Ganymede through a remarkable configuration called a Laplace resonance. For every orbit Ganymede completes, Europa completes exactly 2 and Io completes exactly 4. This 1-to-4 ratio is not coincidence. It arose through billions of years of gravitational interactions, the moons tugging each other into lockstep. The resonance prevents Io's orbit from circularizing, ensuring the tidal flexing never ends. The tidal bulge on Io's surface can fluctuate by up to 100 meters each orbit. Compare that to Earth's ocean tides, which typically shift about 2 meters. The internal friction from this constant stretching and compressing generates enormous heat, estimated at 60 to 160 terawatts. For context, the total power consumption of human civilization is roughly 18 terawatts. Io's tidal heating exceeds that by a factor of 3 to 9. The result is the most volcanically active body in the known solar system. Hundreds of active volcanic centers cover the surface. Eruptions span the full range from steady, persistent lava flows to colossal explosive events that send plumes of sulfur and sulfur dioxide 300 to 500 kilometers above the surface. Io's surface is a phantasmagoria of color. Yellows from elemental sulfur, whites from fresh sulfur dioxide frost, oranges, reds and browns from sulfur compounds in various thermal and radiation modified states, black from fresh silicate lava flows. The whole moon looks like an abstract painting being constantly painted over because volcanic deposits resurface Io so rapidly, impact craters are essentially absent. Io's surface is estimated to be only about 1 million years old on average, making it one of the youngest surfaces in the solar system. The moon is repaving itself continuously. The volcanic features on Io are not towering peaks. They are broad, flat-floored depressions called paterae, surrounded by steep walls. Loki Patera, the largest, stretches about 200 kilometers across and contains an active lava lake. It produces roughly 25% of Io's average heat output. Periodically, the solidified crust on the lava lake sinks back into the molten material below, and Loki's heat output jumps tenfold. Other volcanic features show similar behavior. Tavashtar Patare, during one such overturn event, produced a lava curtain so bright that the camera sensor registered only white, completely saturated by the radiant energy. Despite the flat volcanic features, Io has mountains. Over 100 have been identified, some reaching 17 to 18 kilometers, taller than any mountain on Earth. They are not volcanic in origin. They are tilted crustal blocks, thrust upward by compressive stresses as volcanic resurfacing continuously buries and squeezes older terrain. The mountains tend to be solitary, not part of ranges, and they often occur near volcanic paterae, suggesting a structural relationship between crustal compression and nearby faults. The volcanic plumes are among the most spectacular phenomena in the solar system. Voyager 1 caught the Pele volcano, producing a plume 300 kilometers tall and 1,200 kilometers wide, leaving a distinctive red ring of sulfur deposits on the surrounding terrain. In 2007, New Horizons passed through the Jovian system on its way to Pluto and caught Tvashtar in full eruption, the plume visible hundreds of kilometers above the surface, silhouetted against the blackness of space. The images remain among the most stunning ever captured beyond Earth. Io's composition sets it apart from the other Galilean moons, while Europa, Ganymede and Callisto are made largely of water ice and silicates. Io is almost entirely silicate rock and iron, more like a terrestrial planet than an icy outer solar system body. It has the highest density of any moon in the solar system and the least water of any known astronomical body. Any water Io once had was driven off long ago by the intense tidal heating. The interior is thought to consist of an iron or iron sulfide core surrounded by a silicate mantle that is at least partially molten near the surface, at least 50 kilometers thick. The crust above is continuously recycled by volcanic activity. Io does not appear to have its own magnetic field, suggesting the core is either solid or not convecting in a way that generates a dynamo. Io's volcanism has consequences reaching far beyond the moon. Material ejected by eruptions escapes Io's gravity and enters orbit around Jupiter. It forms a neutral cloud around Io's orbital path and feeds a plasma torus, a donut of ionized particles encircling Jupiter. Material feeds into the torus at about 1 ton per second. The plasma torus rotates with Jupiter's magnetic field, which spins much faster than Io orbits. The torus particles sweep past Io at about 57 kilometers per second relative to the Moon, constantly bombarding and stripping particles from Io's thin atmosphere. The newly ionized particles are captured by Jupiter's magnetic field and absorbed into the torus, which inflates Jupiter's magnetosphere. If the magnetosphere were visible from Earth, it would appear roughly the size of the full moon in our sky. The interaction between Io, the plasma torus, and Jupiter's magnetic field generates the Io flux tube, a concentration of electric current flowing along magnetic field lines between the Moon and the planet. This current carries 1 to 5 million amperes at about 400,000 volts. Where the flux tube strikes Jupiter's upper atmosphere, it produces a bright auroral spot visible in infrared and ultraviolet. Io itself has faint auroras, green from sodium, red from oxygen, blue from sulfur. One final fact about Io that sets the tone for how hostile this environment is. Io orbits right through the core of Jupiter's radiation belt. The surface radiation dose is approximately 3,600 rem per day. A dose of about 400 rem received over a short period is typically fatal for humans. Io receives 9 times that every single day. It is the most irradiated surface of any large body in the solar system. Whatever else Io may be, it is not habitable. Europa. Europa is where the astrobiology story gets serious. It is the smallest of the 4 Galilean moons, 3,122 kilometers in diameter, slightly smaller than Earth's moon. But size is not the point here. What matters is what is inside. Europa's surface is water ice, and it is one of the smoothest in the solar system. There are virtually no large mountains, no deep valleys. Topographic relief rarely exceeds a few hundred meters. If you stood on Europa and looked toward the horizon, you would see a flat, icy plain stretching away in every direction. But that smooth surface is etched with thousands of lines. They are called lineae, and they crisscross the moon in complex overlapping patterns. Many are double ridges, pairs of parallel raised features with a trough between them. They are typically 1 to 2 kilometers wide, but can extend thousands of kilometers in length. The leading theory is that tidal forces pull the icy crust apart, and warmer material from below fills the gaps, freezing into new ice and creating the ridge structures. This is analogous to mid-ocean ridges on Earth, where tectonic plates separate and magma wells up to form new seafloor. Europa's surface is extremely young by geological standards. Crater counts suggest an average age of only 40 to 90 million years. The scarcity of impact craters means the surface is being continuously erased and reformed. Something is actively reshaping Europa's face. The evidence for what that something is has become overwhelming. There is almost certainly a global ocean of liquid salt water beneath the ice. The first strong evidence came from the Galileo spacecraft in the late 1990s. Galileo's magnetometer detected perturbations in Jupiter's magnetic field near Europa, consistent with a large, electrically conducting layer beneath the surface. Salt water is an excellent conductor, and the magnetic signature matched what you would expect from a salty ocean. Europa's icy crust also appears to rotate independently of the interior, completing one full revolution relative to the deeper layers approximately every 12,000 years. This non-synchronous rotation is very difficult to explain unless the ice is floating on liquid, decoupled from the rock below. Regions of chaotic terrain on Europa show ice that has been disrupted, broken apart, shifted, and refrozen in jumbled patterns. Blocks of ice appear to have moved and rotated like ice floes on an Arctic sea before being locked back into place. Something liquid was moving beneath them. The ocean is estimated to be 150 kilometers deep, lying beneath an ice crust, probably 15 to 25 kilometers thick. Europa is 1/4 the diameter of Earth, yet may contain twice as much liquid water as all of Earth's oceans combined. Here is why Europa keeps astrobiologists awake at night. The ocean appears to be in direct contact with a rocky seafloor. On Earth, the most ancient and primitive ecosystems we know thrive around hydrothermal vents on the ocean floor, where superheated mineral-laden water provides chemical energy for life in total darkness, without any contribution from the sun. Entire food webs exist down there based on chemosynthesis rather than photosynthesis. If similar geothermal activity occurs on Europa's seafloor, driven by tidal heating of the rocky interior, then all 3 basic requirements for life, as we understand it, liquid water, chemical energy, and mineral nutrients, could be present simultaneously in the same environment right now. In 2012, the Hubble Space Telescope detected what appeared to be plumes of water vapor erupting from Europa's south polar region, reaching altitudes of about 200 kilometers. The observations were initially controversial because the signals were faint. Subsequent analysis, including re-examination of old Galileo data with modern techniques, found supporting evidence, If confirmed, water plumes would allow a spacecraft to sample ocean material directly by flying through the plume without ever drilling through the ice. NASA's Europa-Clipper spacecraft launched in October 2024 and is expected to arrive in the Jovian system around 2030. It will perform more than 40 close flybys of Europa, carrying a mass spectrometer for analyzing any plume material encountered, ice-penetrating radar to map the structure of the ice shell, cameras and spectrometers for surface imaging, and a magnetometer for constraining the properties of the ocean. The European Space Agency's JUICE mission will also visit Europa, though its primary focus is Ganymede. Juno's flyby of Europa in September 2022, passing within 351 kilometers of the surface, produced some of the most dramatic images of the Moon ever taken. The view along the terminator, the day-night boundary, showed ridges, troughs and craters in sharp three-dimensional relief. The Stellar Reference Unit camera captured a stunning image of a heavily fractured region on Europa's night side, showing complex patterns of grooves, ice ridges, and a dark feature that may represent subsurface disruption. Analysis of the flyby data led to a new hypothesis. Scientists now think pockets of high salinity brine may be trapped within the ice shell itself at relatively shallow depths, separate from the main ocean far below. These brine reservoirs could expand as they freeze, building pressure until they erupt through the overlying ice. If correct, there could be habitable niches not only in the deep ocean, but within the ice crust itself. This hypothesis will be tested by future missions. Europa's surface is stained reddish-brown in many areas, particularly along the lineae and in chaos regions. Spectroscopic analysis indicates salts and sulfur compounds modified by Jupiter's intense radiation. Much of the sulfur originates from Io. Volcanic particles ejected by Io into the plasma torus are swept through Jupiter's magnetosphere and deposited on Europa's trailing hemisphere, the side that faces backward along Europa's orbit, one Galilean moon literally painting another with volcanic fallout across millions of kilometers of empty space. The radiation at Europa's surface is severe, though less extreme than at Io, about 5,400 millisieverts per day, enough to kill a human within a day. Any search for life on Europa must look beneath the ice, where the ocean is shielded by kilometers of frozen water. Europa's thin atmosphere consists primarily of molecular oxygen produced by radiolysis, the process of radiation splitting water ice molecules at the surface. The hydrogen, being lighter, escapes to space. The heavier oxygen molecules accumulate. This oxygen has nothing to do with biology. The atmosphere is far too thin to be breathable, with a surface pressure roughly 100 billion times lower than Earth's. The hydrogen and oxygen that escape Europa's gravity form a tenuous neutral cloud that follows the Moon's orbit around Jupiter. A laboratory study suggests Europa might glow in the dark. Energetic particles from Jupiter's radiation belt penetrate the ice surface, deposit energy in the molecules beneath, and these molecules could re-emit some of that energy as visible light. The color would depend on the ice composition, if confirmed. This glow could serve as a tool for mapping surface chemistry from orbit. No mission has yet imaged Europa's dark side from close range under the right conditions to test this. Europa also has some interesting surface textures. Data from Galileo suggested that the equatorial regions might be covered in icy spikes called penitentes, vertical formations up to 15 meters tall, formed by direct overhead solar radiation causing preferential sublimation. Penitentes exist on Earth in dry, high-altitude regions, though terrestrial examples are much smaller. If present on Europa, they would complicate any future landing attempt. Europa takes 3.5 Earth days to complete one orbit of Jupiter. Along with Io and Ganymede, it participates in the 4-2-1 Laplace resonance. This resonance keeps Europa's orbit slightly eccentric, generating the tidal forces that heat the interior and maintain the subsurface ocean in a liquid state. The surface temperature averages about minus 160 degrees Celsius at the equator and minus 220 degrees Celsius at the poles. The ice crust is as hard as granite, but underneath, kept liquid by tidal energy, lies more water than exists on the entire surface of Earth. Europa's albedo, its reflectivity, is 0.64, one of the highest of any moon. Europa reflects nearly 2/3 of the sunlight that hits it, making it about 5 times brighter than Earth's moon when observed under comparable conditions. Ganymede. Ganymede is a superlative, the largest moon in the entire solar system, diameter 5,268 kilometers, that is 41% of Earth's diameter and 2% larger than Mercury's diameter. For decades, Saturn's moon Titan was thought to be the largest moon because of its thick atmosphere, which extends hundreds of kilometers into space and made the moon appear bigger than it actually is. When Voyager data corrected the solid body measurements, Ganymede claimed the title. Despite being physically larger than Mercury, Ganymede is only about 1/3 of Mercury's mass. The difference comes down to composition. Mercury is dense, packed with iron and heavy silicates. Ganymede is roughly half rock and half water ice, giving it an average density of about 1.94 grams per cubic centimeter compared to Mercury's 5.43. The abundance of water dramatically reduces the average density. Ganymede orbits Jupiter at about 1,070,000 kilometers, completing one orbit every 7.15 Earth days. It is tidally locked, always showing the same face to Jupiter. The name comes from classical mythology. Ganymede was a young Trojan prince whom Zeus, the Greek equivalent of Jupiter, carried off to serve as cupbearer to the gods on Mount Olympus. It seems fitting that the moon Ganymede carries the largest reservoir of water of any body in the solar system. The subsurface ocean on Ganymede is estimated to be about 100 kilometers deep on average, 10 times deeper than the deepest point in Earth's ocean. It contains more water than all the seas and oceans on our planet combined. This ocean lies beneath an ice shell roughly 150 kilometers thick. Below the ocean there may be additional layers of ice in various high-pressure crystalline forms, ice that exists not because of cold temperatures, but because the weight of everything above compresses the water into exotic solid phase. This ice sandwich structure, with the ocean trapped between an upper ice shell and a lower layer of high-pressure ice sitting atop the silicate mantle, has important implications for habitability. If the ocean is isolated from the rocky mantle by a thick layer of high-pressure ice, the water-rock interactions that drive Earth's deep ocean ecosystems cannot occur. Europa, where the ocean appears to contact rock directly, has the edge in habitability assessments. However, if Ganymede's ocean is sufficiently salty, and there's increasing evidence for this, the salt alters the phase diagrams of the ice. Models suggest that with a salty ocean there could be multiple layers of liquid and ice stacked vertically, with the deepest liquid layer potentially in contact with the rocky core. This would change the habitability picture significantly. The research is ongoing. Ganymede has a very thin atmosphere composed primarily of molecular oxygen produced by the same radiation-driven process that creates Europa's atmosphere. The surface pressure is negligible, somewhere between 0.2 and 1.2 micropascals, roughly 100 billion to 500 billion times less than Earth's atmospheric pressure at sea level. A surprise came from Hubble observations supporting Juno's 2021 flyby. Scientists had expected to find abundant atomic oxygen based on earlier ultraviolet data. Instead, they found very little oxygen and significantly more water vapor than anticipated. The water vapor comes from sublimation of surface ice and may indicate that water vapor is more common in the atmospheres of icy outer solar system bodies than previously recognized. Now here is what sets Ganymede apart from every other moon in the solar system. It has its own intrinsic magnetic field, not an induced magnetic effect from Jupiter. Its own internally generated magnetic field, created by dynamo action in a convecting liquid core. It is the only moon anywhere that has one. This was discovered by the Galileo spacecraft during flybys in the 1990s. The evidence was the detection of auroras in Ganymede's tenuous atmosphere, auroras that could only be produced by a magnetic field originating from within the moon itself. The field is about 1% of Earth's strength, but it creates a miniature magnetosphere embedded within Jupiter's far larger one. Why does Ganymede still have an active dynamo? For a moon its size and age, the iron-nickel core should have cooled and solidified long ago, shutting down any magnetic field generation. No other moon in the solar system has managed to keep its core liquid enough for a dynamo. The answer probably involves tidal heating. Although Ganymede is farther from Jupiter than Io or Europa, it is still part of the Laplace resonance and experiences some gravitational flexing. This, combined with heat from radioactive decay, may be keeping part of the core molten. The magnetic field has been instrumental in confirming Ganymede's subsurface ocean without ever going beneath the surface. By monitoring the auroral ovals with Hubble over extended periods, scientists noticed that the auroras did not oscillate as much as expected in response to changes in Jupiter's magnetic field. The best explanation is that a large body of electrically conducting fluid, a salty ocean beneath the surface, generates its own field that partially counteracts the external variations. This magnetic friction constrains the depth, thickness, and conductivity of the ocean. Ganymede's surface tells a story of two different epochs. About 1/3 is covered by dark, heavily cratered terrain, ancient, roughly 4 billion years old, similar in appearance to Callisto. The other 2/3 consists of lighter, younger terrain, marked by long grooves and ridges, some up to 700 meters high and thousands of kilometers long. This grooved terrain is estimated to be about 2 billion years old based on crater count. The grooved terrain probably formed through tectonic stretching, possibly during a period of enhanced tidal heating in Ganymede's past. The stretching pulled the surface apart, creating parallel ridges and troughs. This represents a phase of geological activity that has since quieted but left its signature across 2/3 of the Moon's surface. When Juno flew within about 1,000 kilometers of Ganymede on June 7, 2021, it captured the best images of the Moon since the Galileo mission. Resolution approached 1 kilometer per pixel. The sharp contrast between dark ancient terrain and lighter grooved terrain was vividly apparent, along with individual craters and structural features. The Tross crater stood out as a particularly bright feature, its ice-covered interior reflecting sunlight brilliantly. The Stellar Reference Unit camera captured Ganymede's dark side, illuminated only by Jupiter shine at resolutions between 600 and 900 meters per pixel. Craters, lineations, and terrain boundaries were clearly visible in what is essentially moonlight photography taken by a star-tracking navigation camera. The European Space Agency's JUICE mission will eventually enter orbit around Ganymede, making it the first spacecraft to orbit any moon other than Earth's own. JUICE launched in April 2023 and is expected to reach the Jovian system in 2031, with Ganymede orbit insertion following a few years of Jupiter system exploration. It carries ice-penetrating radar, cameras, spectrometers, a magnetometer, and other instruments designed to study the Moon's ocean, interior, surface, and atmosphere comprehensively. Callisto. If Io is fury, and Europa is mystery, and Ganymede is grandeur, then Callisto is patience. It is the most ancient and least changed of the four, a frozen record of conditions that existed at the very dawn of the solar system. Callisto is the third largest moon in the solar system, 4,821 kilometers in diameter. That is only 58 kilometers less than Mercury's diameter, though Callisto has only about 1/3 of Mercury's mass because it is made of lower density material, roughly half rock and half ice. It orbits much farther from Jupiter than the other 3 Galilean moons at an average distance of 1.88 million kilometers, completing one orbit every 16.7 Earth days. Even at this distance, it is tidally locked, always showing the same face to Jupiter. Unlike Io, Europa and Ganymede, Callisto is not part of the Laplace resonance. It orbits independently without commensurate gravitational interactions with the other large moons. Scientists do not believe it was ever part of the resonance. This independence has a fundamental consequence: minimal tidal heating, and without tidal heating there is no energy source to drive geological activity. Callisto is geologically dead. There are no volcanoes, no tectonic plates, no resurfacing processes, no mountains formed by internal forces. The surface is approximately 4 billion years old, dating to the late heavy bombardment era of the early solar system, and it is saturated with impact craters, more craters per unit area than any other object we have closely observed. At this point, any new impact crater will likely overlap older ones, because there is simply no room left. Without geology to erase them, craters have accumulated for the entire history of the solar system. This makes Callisto invaluable as a time capsule. Its surface preserves a record of impact conditions from the earliest era, essentially untouched. The most impressive features are enormous multi-ring impact structures. Valhalla is the largest. It has a bright central region about 600 kilometers across, surrounded by concentric fracture rings extending to a total diameter of approximately 3,800 kilometers. It is the largest multi-ring impact structure in the entire solar system. The bright central area represents where the impactor punched completely through the thin icy crust and fresh ice refroze from below. The concentric rings are fractures in the brittle shell propagating outward from the impact site. Asgard is the second largest, measuring about 1,600 kilometers in overall diameter. Both structures owe their appearance to Callisto's particular surface composition, a thin brittle ice shell over softer material beneath. The ice cracked concentrically while the underlying material flowed and healed, preventing the formation of the deep bowl-shaped craters you would see on a purely rocky body. Many of Callisto's smaller craters are remarkably shallow compared to similar-sized craters on the Moon or Mercury. Over billions of years, the ice has undergone viscous relaxation, slowly flowing under its own weight to fill in depressions. Even the largest impact basins have been substantially flattened by this process. The Lof impact structure, for example, is over 100 kilometers wide, but only about 600 meters deep. Some craters show unusual features. Har crater has a dome in its center rather than the typical central peak. Tinder crater has a pit instead of a peak. These may result from the particular properties of Callisto's thin ice crust and the soft or liquid substrate beneath it. Across large areas of the older terrain, Callisto has a distinctive knobby texture. Bright icy hills rise from darker, lower lying plains. The hills are the degraded remnants of billions of ancient crater rims worn down over the eons by micrometeorite bombardment and slow sublimation of ice. The hilltops are bright because rocky debris has slid down their slopes over time, leaving relatively pure ice exposed at the peaks. The darker plains between them represent accumulated dust and rock left behind as ice sublimated. Callisto has a very thin atmosphere composed primarily of carbon dioxide, with possibly some molecular oxygen, though oxygen has never been directly detected. The atmosphere is so tenuous that individual molecules essentially never collide with each other. Atmospheric loss processes would strip it away in about 4 years. Scientists believe the atmosphere is continuously replenished by sublimation of carbon dioxide ices on the surface. The Galileo spacecraft detected perturbations in Jupiter's magnetic field near Callisto, consistent with a conducting layer beneath the surface, possibly a subsurface ocean. The evidence is less compelling than for Europa or Ganymede, and alternative explanations have been proposed. If an ocean exists, it is deeper and likely smaller than those on its neighboring moons, separated from the rocky interior by layers of ice. The interior of Callisto is also unusual. Unlike the other Galilean moons, Callisto does not appear to be fully differentiated. That is, its rock and ice may not be completely separated into distinct layers. This is surprising for a body its size and age, and it may indicate that Callisto never experienced enough internal heating to allow full differentiation. This is consistent with its exclusion from the orbital resonance and the resulting absence of tidal heating. The prospects for life on Callisto are considered less favorable than on Europa or Ganymede. Without tidal heating, there is insufficient energy. Without confirmed water-rock contact, there are insufficient mineral nutrients. No plumes or vents have been detected that might indicate active exchange between any subsurface water and the surface. But Callisto has another potential role. If humanity ever establishes a sustained presence in the outer solar system, Callisto may be the best location for a base. At 1.88 million kilometers from Jupiter, Callisto orbits beyond the worst of the radiation belts. The surface radiation environment is thousands of times less hostile than at Io or Europa. A human could survive on Callisto's surface with reasonable shielding, which is absolutely not the case closer in. The abundant water ice can be processed into drinking water, breathable oxygen, and hydrogen fuel. The geologically stable surface has no volcanism or tectonics to worry about. The absence of large mountains or deep trenches makes surface travel straightforward. The low gravity, about 0.126 G, makes launching spacecraft relatively easy. A close flyby of Jupiter on departure could provide a significant gravity assist for missions heading deeper into the outer solar system. This is futuristic planning by any measure, but if our species is around in a few centuries and is serious about exploring beyond Mars, Callisto will be on the short list of destinations. Several NASA concept studies have examined this possibility. The European Space Agency's JUICE mission has planned several close flybys of Callisto during its time in the Jovian system. These flybys will provide more detailed information about the Moon's interior structure, surface composition, and whether a subsurface ocean truly exists. JUICE carries ice-penetrating radar that could help resolve this question. Now let us pull back and trace the history of our exploration of Jupiter, mission by mission, because the story of what we thought we knew versus what we actually found is a story of constant surprise. Before the space age, everything we knew about Jupiter came from telescopes. We could see the bands, we could track the Great Red Spot, we could identify the 4 Galilean moons and measure their orbits. Spectroscopy told us the atmosphere contained hydrogen, helium, methane, and ammonia. We knew the approximate size, mass, and orbital period, but everything beyond the visible surface was speculation. The first spacecraft to visit Jupiter were Pioneer 10 and Pioneer 11 in 1973 and 1974. Their instruments were primitive by modern standards, but they made the first direct measurements of Jupiter's magnetic field, radiation environment, and atmospheric structure. Pioneer 10 confirmed that Jupiter's radiation belts were far more intense than anything near Earth, 10,000 times stronger. This was a rude awakening and shaped the design of every subsequent mission. Pioneer 11 confirmed that Io's surface was silicate rock rather than water ice and detected a thin atmosphere around the Moon. Pioneer 10 lost some data from Io when Jupiter's radiation interfered with the spacecraft's command system. Voyager 1 and 2 arrived in 1979 and transformed our understanding of the entire Jovian system. Voyager 1 flew within 20,000 kilometers of Io and saw a landscape that nobody had predicted. Vivid colors, zero-impact craters, mountains taller than Everest, and volcanic plumes actively erupting from the surface. It was the first direct observation of active volcanism anywhere beyond Earth, excluding cryovolcanism. Voyager 2, passing 4 months later at a greater distance of about 1 million kilometers, confirmed that the volcanoes remained active, with 7 of the 9 plumes Voyager 1 had seen still erupting. The Voyager probes also provided the first detailed images of Europa, Ganymede, and Callisto, revealing Europa's cracked icy surface, Ganymede's two-tone terrain, and Callisto's crater-saturated face. The Galileo orbiter arrived in 1995 and spent 8 years in the Jovian system. Despite serious mechanical problems, including a stuck high-gain antenna that reduced data transmission rates by a factor of more than 100, Galileo made fundamental discoveries. It dropped an atmospheric probe into Jupiter that transmitted data for 57 minutes as it descended, finding far less water than expected, a mystery still being investigated. The orbiter mapped the surfaces of the Galilean moons in detail, discovered Ganymede's magnetic field, found strong evidence for subsurface oceans on Europa and Ganymede, and possible evidence for one on Callisto, observed Io's volcanic eruptions at close range, and confirmed the composition of volcanic material as silicate magmas rich in magnesium, similar to terrestrial lavas. New Horizons passed through the Jovian system in February 2007, using Jupiter's gravity to accelerate toward Pluto. It captured the famous images of Trefstar erupting on Io and gathered data that complemented earlier missions. Its instruments were tested and calibrated during the flyby, preparing for the Pluto encounter 8 years later. And then Juno. Juno launched from Cape Canaveral on August 5, 2011, after a 5-year journey including an Earth gravity assist in October 2013. It arrived at Jupiter on July 5, 2016. It entered a highly elliptical polar orbit designed to bring it as close as 4,100 kilometers above Jupiter's cloud tops at periapsis, while swinging out to over 8 million kilometers at apoapsis. Each orbit in the primary mission took 53 days. Juno's polar orbit was chosen for multiple reasons. It allows the spacecraft to fly over both poles, regions never well observed before. It threads through the gap between Jupiter's atmosphere and the inner radiation belt, minimizing radiation exposure. And the close approaches enable precise gravity measurements that reveal the planet's interior structure. The spacecraft is distinctive. 3 enormous solar panels, each about 9 meters long, give it a total span of roughly 20 meters. It is the first solar-powered spacecraft to operate at Jupiter's distance from the Sun, where sunlight is only 4% as intense as at Earth. Even with those large panels, Juno generates only about 400 watts. The spacecraft spins at about 2 rotations per minute, stabilizing itself and sweeping its instruments across the planet during each close approach. Juno carries 9 science instruments, plus JunoCam, a visible light camera included primarily for public engagement. The instruments include a microwave radiometer for probing atmospheric structure at depth, a magnetometer for mapping the magnetic field, a gravity science experiment using Doppler shifts in the radio signal, ultraviolet and infrared spectrometers and imagers for studying auroras, and particle detectors for the radiation environment. The primary mission was planned to end after 35 orbits. Multiple extensions have been approved, the most recent extending operations through September 2025, with approximately 77 total orbits planned. The extended mission added close flybys of 3 Galilean moons: Ganymede on June 7, 2021, Europa on September 29, 2022, and multiple Io passes in 2023 and 2024. What Juno discovered overturned decades of assumptions. The atmosphere extends 3,000 kilometers deep, far beyond the few hundred kilometers previously modeled. The fuzzy core replaced the neat solid sphere everyone expected. The magnetic field is more irregular than any model predicted, with secular variation detected for the first time. A previously unknown equatorial radiation belt was discovered. Geometric polar cyclones, 5 at the South Pole and 8 at the North, appeared in stable configurations that no simulation had produced. The ammonia distribution was especially puzzling. Scientists expected ammonia to be well mixed throughout the atmosphere. Instead, the microwave radiometer found it concentrated in a narrow equatorial column extending at least 350 kilometers down and depleted at other latitudes. This pointed to previously unknown atmospheric transport mechanisms. Juno solved the mystery of Jupiter's lightning. Voyager had detected radio emissions consistent with lightning in 1979, but at frequencies different from terrestrial lightning, leading some to question whether it was truly lightning. Juno detected emissions at all frequencies, including the familiar megahertz range, confirming that yes, Jupiter has lightning, but it occurs preferentially near the poles, especially the North Pole, the opposite of Earth, where tropical thunderstorms dominate. On Jupiter, the internal heat, not the Sun, drives convection, and the polar regions have the greatest temperature contrast between the warm interior and cold upper atmosphere. Even more surprising was the nature of the storms. The lightning-producing thunderstorms occur at altitudes and temperatures where pure water storms are impossible. Juno found that ammonia acts as an antifreeze, combining with water to form a liquid solution at temperatures below -88 degrees Celsius. These ammonia water storms produce a form of precipitation that scientists have called mush balls, slushy hailstones of water-ammonia mixture coated in water ice. As mush balls form high in the atmosphere and fall to greater depths before evaporating, they transport ammonia downward, explaining its depletion at intermediate altitudes. The radiation environment turned out to be better than feared in some regions and surprising in others. The radiation in Juno's orbital corridor was about 10 times lower than worst-case predictions, which is good news for the spacecraft's longevity. But the discovery of the equatorial radiation belt, previously unknown, shows that Jupiter's radiation environment is more complex than models had captured throughout the primary and extended missions. Juno's cameras have produced images of Jupiter that are genuinely breathtaking. The close-up views of storms, vortexes, cloud formations, and polar features are unlike anything previously obtained. At the resolution Juno achieves, you can see individual convective cells in the cloud deck. The white specks visible in many images are pop-up clouds, towers of water or ammonia ice rising above the main cloud layer, casting shadows that reveal their elevation. They look tiny in the images but are actually over 50 kilometers across. Jupiter is so large that features the size of a small country appear as mere specks. Due to the freezing temperatures at cloud-top altitudes and the icy composition of these pop-up clouds, it may very well be snowing on Jupiter. Not water snow as we know it, but ammonia ice crystals falling through a hydrogen-helium atmosphere under 2.5 times Earth's gravity. The mind struggles with the scale and alienness of it. The Great Red Spot, examined directly by Juno, extends at least 350 kilometers below the visible surface, and likely much farther. It is cooler above and warmer below compared to its surroundings, with the deep warmth probably driving the storm's persistence. Whether it is truly permanent remains unknown. We have only observed it for about 400 years, which is geologically insignificant. It could last another 4 centuries or vanish next decade. We do not understand it well enough to predict. At the conclusion of its mission in September 2025, Juno will be deliberately deorbited into Jupiter's atmosphere, where it will burn up and disintegrate. This is standard procedure under NASA's planetary protection guidelines, designed to prevent any terrestrial biological material on the spacecraft from potentially contaminating the moons, particularly Europa, where conditions might support life. Galileo followed the same protocol in 2003. Both spacecraft were sacrificed to the planet they studied, consumed by Jupiter's atmosphere and crushed by its pressure. But the exploration of Jupiter does not end with Juno. 2 major missions are currently en route to the Jovian system. The European Space Agency's JUICE mission launched in April 2023 after a complex series of gravity assists including flybys of Earth, Venus and Earth. Again, it will arrive at Jupiter in 2031. JUICE will spend several years studying Jupiter's atmosphere and magnetosphere while performing close flybys of Europa, Callisto and especially Ganymede. It will eventually enter orbit around Ganymede, becoming the first spacecraft to orbit any moon other than Earth's own. JUICE carries 11 scientific instruments, including cameras, spectrometers, ice-penetrating radar, a magnetometer, a laser altimeter, and particle detectors. NASA's Europaclipper launched in October 2024 and will arrive in the Jovian system around 2030. This dedicated Europa mission will perform more than 40 close flybys of Europa. Its instrument suite is optimized for characterizing Europa's ice shell, ocean composition, and potential habitability. It carries a thermal emission imaging system, ice-penetrating radar, a mass spectrometer for analyzing any plume material encountered, and a comprehensive array of cameras and spectrometers. By the early 2030s, 2 sophisticated spacecraft will be operating simultaneously in the Jovian system, each approaching the science from different angles. Together they have the potential to answer questions that have tantalized scientists for decades. How thick is Europa's ice? What is the ocean's composition? Is there geothermal activity on the seafloor? Are there brine reservoirs in the ice shell? Does Ganymede's ocean contact rock? What is the internal structure of Callisto? And behind all of these specific questions lurks the big one, the one that connects planetary science to the deepest human curiosity. Is there life in those oceans? Nobody knows. Nobody can know until we get there with the right instruments. But the ingredients are present: liquid water, probably salty rocky surfaces where water rock chemistry can occur, at least on Europa, energy from tidal heating, organic compounds delivered by comets over billions of years. Chemistry that has had 4.6 billion years to do whatever chemistry does when conditions are right. Life on Earth has proved astonishingly adaptable. It exists in boiling hot springs at 120 degrees Celsius, in subglacial lakes sealed under kilometers of Antarctic ice for millions of years, in rocks kilometers below the surface where bacteria extract energy from chemical reactions with the stone, on the ocean floor around hydrothermal vents in complete darkness at crushing pressure, surrounded by toxic chemicals. Every place on Earth where liquid water persists, life has found a way. Can it do the same on Europa? Can some form of microbial life persist in a dark, salty ocean, warmed by gravitational tides, fed by minerals from a rocky seafloor, billions of kilometers from the sun? The honest answer is we do not know. But for the first time in human history, we have missions specifically designed to find out, and they are already on their way. Whatever the answer turns out to be, it will reshape our understanding of life's place in the universe. If we find life on Europa, even microbial life, it means biology is not a fluke. It means life arises wherever conditions permit. That changes everything we think about the hundreds of billions of planets in our galaxy and the trillions in the observable universe. And if we look and find nothing, that is significant too. It means the origin of life may require conditions more specific, more delicate, more improbable than we currently believe. Either answer is profound, and Jupiter is where we go to find it. Let us step back now and consider Jupiter as a whole system, because one of the things that makes it so extraordinary is how all the pieces connect. Jupiter's rapid rotation and massive size generate the atmospheric banding. The bands create jet streams. The jet streams breed storms. Some storms persist for centuries. The rotation also stirs the metallic hydrogen interior, generating the most powerful planetary magnetic field in the solar system. The magnetic field creates radiation belts that shape the environment around the planet for millions of kilometers. The magnetic field interacts with Io's volcanic output, creating the plasma torus that encircles the planet. The plasma torus feeds the auroras. The auroras are permanent, powered from below by the rotation of the magnetosphere itself. Io's volcanism exists because of tidal heating. The tidal heating exists because of the Laplace resonance. The resonance exists because Io, Europa, and Ganymede gravitationally tugged each other into lockstep over billions of years. The same tidal forces that drive Io's volcanoes maintain Europa's subsurface ocean in a liquid state. They may be keeping Ganymede's core molten enough to generate a magnetic field that by rights should have died long ago. Jupiter's gravity shapes the asteroid belt, influences the orbits of comets, and may shield the inner solar system from a higher rate of catastrophic impacts. Everything connects. The mass drives the gravity drives the tides drive the geology drives the chemistry, and the chemistry, under the right conditions, might drive biology. Jupiter is not just a planet, it is an engine, a system, a laboratory for understanding how solar systems work and where life can emerge. It is the most influential non-stellar object within several light years, and we have been studying it seriously for only about 50 years. 50 years of investigation versus 4.6 billion years of history. We are at the very beginning. Every mission has overturned previous assumptions. Every set of new data has revealed complexity where we expected simplicity. The core we thought was solid turned out to be fuzzy. The atmosphere we thought was shallow extends thousands of kilometers. The storms we thought were surface features reach to unknown depths. The moons we assumed were dead ice balls turned out to harbor vast oceans, active volcanoes, magnetic fields, and perhaps the conditions for life. The history of Jupiter research is a history of humility. Nature is always more complicated than our models, more surprising than our predictions, more creative than our imagination. The next decade will bring data from JUICE and europaclipper that will take years, perhaps decades, to fully analyze and understand. New questions will emerge that we have not thought to ask. New phenomena will be discovered that no model anticipated. Jupiter will surprise us again. It always does. Somewhere beneath the fractured ice of Europa, in a dark saltwater ocean warmed by the gravitational embrace of the largest planet in our solar system, something may be happening that we have never seen before. Not on the scale of whales and forests, probably something small, microbial, perhaps just the faintest chemical signature of metabolism, a molecule out of place, an energy gradient being exploited by something that, by any reasonable definition, is alive, or perhaps not. Perhaps Europa's ocean is sterile, a vast dark body of salt water, where chemistry proceeds without biology, where the ingredients are present but the spark never caught. That would be its own kind of answer, profound in its own way. We are about to find out. The spacecraft are already flying, the instruments are calibrated, the questions are defined. Jupiter, the king of planets, has kept its secrets for 4.5 billion years. In the next decade, we are going to pry some of them loose. And whatever we find, it will change how we think about our place in the cosmos. Because Jupiter is not just another world in the sky, it is the key to understanding whether worlds like ours are common or rare, whether life is an inevitable consequence of chemistry or an improbable accident, and whether the universe is as empty as it sometimes appears or as full of surprises as Jupiter has always turned out to be. The story of Jupiter is the story of science itself. We look, we measure, we build models, and then nature shows us something we never expected, and we start again a little wiser, a little more humble, and a lot more curious than before. The King of Planets is not done with us yet.